I'm going to go through some work that I did with Stefan Svensson on horizontal fire ventilation. And this PowerPoint is originally presented by Stefan, but I have added quite some things about pressure and pressure buildup and pressure differences. Stefan starts by asking, what is a fire and rescue operation? And he has a very long definition. It's a thing where you go and everybody is connected and so. The key word here is dynamic environment. Everything is changing. The fire is changing, the suppression is changing, and the ventilation and all kinds of things are changing all the time. And that's basically it. He's basically saying that every situation is different. And maybe that summarizes what we were talking about earlier, that some people find that high pressure is better than low pressure and so and so. It just depends on the situation. So the situation, there's a dynamic environment, everything is changing. No situation is exactly the same. Everything is different. So that's what we're talking about. And we come from a department at the engineering faculty at the university called systems safety. So we have a look at systems very much. And a system is a component of very many things that can change interactively. And if we apply that to try to be very simple, if we apply that to firefighting, we can say you can have an offensive attack with people with breathing apparatus. You can have suppression with water from the inside or the outside. You can have ventilation or a combination of all these at different times. And then also you have the fire, and the fire can change all the time. So this is a system which is continually changing and developing. And and Stefan's point is this, fire behavior is a vital part of the operation, but it's just one part. And that's what he's saying here. The suppression is also a vital part in the whole system, but it's just one part. And the ventilation, which we are going to talk about today, the ventilation part of it, it's only one of the parts. So we have to remember that there are very many other things that are happening than fire ventilation. And even though we are going to be talking about ventilation today. And the question we are going to ask, can we use fans or some kind of horizontal ventilation to put out the fire or help extinguish the fire? And usually we say that what we want to do is to vent the smoke or the hot gases in a controlled fashion. We want to control it. And we usually do it to reduce the impact of heat or to facilitate the rescue operation or to stop the spread of fire. And finally, often we do it at the end of the rescue operation. There's a lot of smoke still in the house. We put up some positive pressure fans and blow the smoke out just to clean up, basically. And so what we do, we create openings, either existing or new ones. And the pressure always goes, the flow always goes from high pressure to low pressure. Can't really change that. It's like the law of gravity. It always works in the same direction. It's the same with flow. It follows the pressure, from higher pressure to lower pressure. Always. if we have a look at pressures in buildings due to a fire, we usually distinguish between two different types of pressure, so to speak. One type is the type of pressure that occurs because of thermal expansion. You have a closed room, you put in a lot of energy in this room, and the gases expand. The room does not expand. It's not like a balloon. And therefore, the pressure increases due to thermal expansion. This requires that you actually have very little openings. But as soon as you have an opening, then this kind of pressure isn't most important. The pressure that's most important is due to buoyancy or due to density difference. When I say pressure difference because of buoyancy, it's the same as saying pressure difference because of density differences. And this is very often the case that we're talking about. And so this is what happens in a room with a very small opening. You will have expansion of the gases, and therefore there's a positive pressure in the whole room. The gases expand, and there will be just outflow. There's no inflow. It's just outflow if there's a very small opening. But if there's a big opening, if the door is open, then you will have inflow and outflow. And these two pressure situations are a little bit different. And this pressure situation, the flow occurs because of density differences. The density here, it's much lower, or this is much hotter than out here. And this will create a flow out and in. Let's talk a little bit about pressure. Say just a few words about pressure. The pressure drives the flow. And pressure is measured in Pascal. And Pascal is actually, it's a Newton per square meter. And Newton is kilogram meters per second square. Meters per second squared is the acceleration, often the acceleration of gravity, 9.81 meters per second squared. So that's the acceleration. So see, this piece of paper here is 10 grams or something. When I put it on this table, it will exert 1 Newton per square meter, because it's I will have to multiply by 9.81, and then I will have to divide. This is per square meter. So this paper actually is 1 Pascal. This paper puts 1 Pascal force, or 1 Newton per square meter force on this table. So that's very light. That's very little. That's nearly nothing. And at sea level, the normal atmospheric pressure is 101,300 Pascal. So here, resting on my head, is a force of 101,000 newtons per square meter. Where does this weight come from? Why can't I feel it? It's the weight of air all the way from the atmosphere and down to here. It's resting on my head. It's 101,300 Pascal, or 1 atmosphere. We can measure pressure in bars and millibars and so many meters of water and so and so. So what complicates the discussion sometimes is that you can talk about pressure in very many different units. Oh, it's millibar. Oh, it's atmospheres. It's Pascal. It's this, it's that. In science, we usually just use Pascal because it's Newton and it's kilograms and so on. So we use Pascal. It's 101,000 Pascal, but some people think it's much more convenient to talk about atmospheres and so and so. But I'm going to talk about pascals. And the great information here is this, that there's 100,000 pascals here. This tiny little paper is 1 Pascal. And it is this tiny force that drives the flow. So in this room now, we have 20 degrees. Outside, we have 0 degrees. So there is a difference in densities, which creates a difference in pressure, a pressure difference. And therefore, and actually, when we calculate it, it's only a few pascals. It's 3 or 4 Pascal difference in here and out there. It's only 3 or 4 Pascal. That's tiny. But it completely dominates the flows in this room. So this room now, as we talk, will change completely. The whole volume of this room will be changed 3 times during this lecture. During this 1 hour, all of the cubic meters of air in here will go out and new air will come in 3 times. 2 times maybe. 2 or 3 times. Why? Because of the 2 or 3 Pascal, because 20 degrees, 0 degrees. So it's quite a lot of magic that so little force. This is 1 Pascal. So 2 or 3 Pascal difference will move all this. So it's only, usually it's only just a few Pascal that drive the flow. If we increase the temperature here up to 100 degrees or something like that, then the density will be much lower and there's much greater density difference and will come up to a few tenths of Pascals. So it will be faster flow. And the flow will sort of, it'll seep in at the lower part and seep out at the upper part. Nothing is open here. Still, we will have this exchange of, complete change of air. And so the pressure differences in a building are an extraordinarily small fraction of atmospheric pressure. Much, much less than 100 Pascal. Usually only a few Pascal. Usually when we talk about pressure, it's the same pressure. It's just if we're in the center of the room and the air is not moving at all, there's no velocity of the air right here, we talk about hydrostatic pressure. And we can calculate it or find it out by saying at what height is this point, and we can figure out that's the weight of this. It has this density, and the gravitational constant, 9.81, is pulling on it, and there's a certain Pascal pressure. But when I go out to the opening, down at the threshold here, I will have a velocity, a certain velocity. And I describe the velocity in this way. It's a hydrodynamic pressure difference. So the pressure difference between this room and outside will be expressed by a certain velocity out through this little opening. And I express it in this way. And to link these two, we usually say velocity is equal to, velocity squared is equal, this is equal to that, we say. This is equal to that. And therefore, we can calculate the velocity. Velocity equals, and we can figure out how many meters per second. And if we know the area, we can say how many cubic meters per second, and therefore how many kilograms per second. are going out and coming in. So this is the way we link the pressures, and this is the way we then calculate how many kilos are going in, how many kilos are coming in and going out. One more thing about pressure. Now let's say that I have a glass of water. The weight of the air increases all the way down. It keeps increasing. So the pressure increases all the way down to the floor. But at this point, suddenly, the density changes. So this is the weight of column of air. And then suddenly I hit this water. The density of the water is 1,000 times higher than the density of this air. And therefore, the weight suddenly increases, and we have an increasing pressure all the way here. Now it's no longer 1 Pascal from this paper, but it is far many more Pascal per meter. Now this glass is it's per square meter. This glass is not 1 square meter, so it's only a little bit of a force, but still. So what I'm trying to say is that the pressure increases all the way through the atmosphere, all the way down like this. And when we apply this to a building, but it does change when we change the density of the fluid. And that's the key to thinking about the hot air in here and the cold air outside. And this is what happens if we have let's say that we have a little opening right under the door. Say that we have a little opening up here also. This is the normal weight of the column of air coming down from the atmosphere, and it's cold air, so it's pretty heavy. It's heavy cold air. When I draw it here, it comes down here to the room, but here we have a different density. We actually have a hotter air. They're lighter, much lighter air. So therefore, this density comes down here, but breaks and is a much lighter. And when I do the density difference, the pressure difference between the pressure here and the pressure outside, I get this. So what I get is I get let's say a positive pressure out here that pushes air in. But up here, I have a negative pressure that draws things out. We can turn this around, and I can say, oh, now I'm going to stand inside. Then the pressure is negative and positive. But if I'm outside, I say the pressure is positive pushing and negative drawing. Okay? So this is a very typical, and this is what's happening right here, right now. At the bottom of this, at the floor level of this room, we have quite a heavy, now I'm standing inside the room, so there is positive pressure down here pushing the air out through this slit. And then it pushes less and less and less and less until it doesn't push anything out, but starts sucking things in. Sorry, it's the wrong way around. It's actually the air is coming in here, and it's pushing out there. So it's negative pressure down here. It's drawing the air in, cold air in, mixing, and then pushing it out up here. So at some point, we have something which we call the neutral layer, where there is nothing going in or out, and so and so. So we call that neutral plane, the neutral plane. And And we can use this hydrodynamic and hydrostatic pressure to simply calculate the velocity in, calculate the velocity out. If we know the velocity and we know the area, then we can say area square meters times velocity meters per second, that becomes cubic meters per second. So if I know the velocity, I can calculate the volume flow, the cubic meters per second, and then I can multiply by density, kilograms per cubic meter, and I get mass flow, I get kilograms per second. So I know how many kilograms are going out, how many kilograms are coming in. If I know how many kilograms are going out, then I also know how many kilograms are coming in. Why? The conservation of mass. The conservation of mass. Mass does not disappear. If I get 5 kilos going out, I gotta have 5 kilos coming in. There's no other way. You can take this discussion up with God Almighty if you wish, but this is the way it is. So the mass balance does this. And so this was a few words about this, and so a few words about this neutral plane. Let's say I have 20 degrees in here and 0 degrees outside. If I have a very big opening, I don't need a lot of pressure. The opening is big. I get a lot of cubic meters per second flowing very, very calmly in through this opening. But up here, I have a tiny opening. So I need huge pressure to push it out through this tiny little opening. So my neutral layer is going to be very low. I'm going to have a heavy pressure up here. Let's turn this around. So here, 20 degrees, 0 degrees. I'll have to suck in I have to have a huge pressure here to suck in all this air, just a little bit up here to get it out. So we can ask, what happens if I close it? If I close this, what will happen to this pressure diagram? Well, I'm afraid it'll move just a little bit here until there's 0. If there's 0 coming in, there's 0 going out. So this is not something that I figured out. This is Bernoulli figured this out about 300 years ago. This is extremely important for fire ventilation. If we don't have enough inlet air, we don't get anything out, even though we open the whole roof. It's not going to come out if we don't get anything in. Mass balance. So if nothing's coming in, nothing's going out. You know this thing, you're smoking, you have a can of Coke or something, empty. You smoke your cigarette, you put the butt into the can, and you say, right, now this air is going to heat up, there's going to be a lot of smoke in here, but no smoke comes out. The smoke doesn't actually come out of the Coca-Cola can. It stays in there. Why? Because there isn't any inlet. If I drill a little hole down there, whoops, I'll get air in, smoke out. So this principle is very important when we talk about fire ventilation. These things here. We want to have a situation like this. We want the neutral plane somewhere in the middle. We want to get fresh air in and get the smoke out. The size of these openings is very, very important. Now we'll continue. And the wind. Now we get to the wind. So the wind is blowing this way, which means that the roof, the roof of this house will be wanting to get off, or there will be leakage of air coming out here. So, but on this side of the building, we will have positive pressure. The smoke will not want to go out here. The smoke will want to go out here and here and here, but not on this side. The smoke usually exerts about a few Pascal. No, the wind is maybe a few Pascal. 1, 2, 3 Pascal, something like that. That's similar to the effect of the fire and the heat inside. That's maybe from 3 to 10 Pascal for 100 degrees temperature difference, something like that. So if we're going to fight with the wind, it's not good. So we have to try to use the wind to help us with it. This, of course, you know, but it's good to know that Pascal and Bernoulli and those guys, they figured this out a few hundred years ago. So let's say that there is an opening. There will be a flow of gases between rooms with different pressure. If there's different pressure in the rooms, there will be flow. And the flow will go from higher to lower. And when we add a fan, it doesn't change this difference. It changes the pressure, but not this fact. And we have to consider this. If the fire is fuel controlled, then the situation is somewhat simpler. When we say fuel controlled, it means that it's controlled by the amount of fuel in furniture or whatever it's burning. But if it is ventilation controlled, so we have a lot of fire, a lot of fuel, but we have limited air coming in, and the size of the fire is limited by the ventilation, then we have to be very, very, very careful with applying fire ventilation. So because the fan pushes air to the fire, and we have to be very careful about this, and we have to be ready with the suppression and ready with all kinds of, we have to think about this very carefully, preferably know where the fire is, to be able to create an opening close to the fire and things like this. So fuel control is actually, we say that, I'm not going to go into this, just going to say that wood produces 17 megajoules per kilogram of wood, polystyrene quite a lot more, but most products are somewhere between here. So it's so much energy, megajoules, for every kilogram of stuff, okay? And maybe we have a lot of this, but if the limitation is access to oxygen or air, then we say that approximately 13 megajoules per kilogram used oxygen. So let's say that if you have a 2 megawatt fire, which is perhaps 2 of these chairs or something, a bit more, then we need a door opening. An ordinary door with an airflow of about 1 meter per second can produce 5.2 megawatts. So what happens here is that when we open up, the pressure distribution in the building completely changes momentant. It just does it, right? Temperature takes always time to react. Pressure, like this. And suddenly there's a completely different picture. Smoke and hot gases flow out and fresh air comes in, In the fuel-controlled fire, there's no immediate or obvious distinct influence on the fire, but we have to be ready with a high-pressure hose or the low-pressure hose. We have to be ready. But in the ventilation-controlled fire, there will be I say immediate, sometimes it takes maybe 20 seconds for the oxygen to get in, but it's an order of seconds. We have to be absolutely ready to do stuff, absolutely ready, and we have to be very careful if we've had a lot of unburnt gases. Such disasters happen very seldom, but when they happen, the consequences are absolutely terrible. So be careful if we have underventilated fire. You have to think about all kinds of things like, where is the fire? Is there anybody in the house? If there are human beings in the house, we're gonna be very, very careful, and we're gonna preferably open up close to the fire, away from the wind, and be ready with the firefighters to attack immediately. But so we will have there will be an immediate influence on the fire. The fire will increase in its intensity, and there will be a more rapid flame spread and all that stuff. So important basic principles on fire ventilation, I would say, is it fuel controlled? Is it ventilation controlled? And we have to coordinate with everything else. And we want to ventilate as early as possible during an operation to diminish everything. But ventilation will always affect the fire in some way. And even though we add a fan, doesn't change this fact. It'll maybe change things faster, but it. So I'm going to say a few words about the Bernoulli principle. Bernoulli actually lived in Antwerp, I think, in 1700. And then they moved to this Bernoulli family. They moved to Switzerland, and that's where Daniel Bernoulli came up with the Bernoulli principle about 300 years ago. And he basically said, if stuff is happening here, then that has a complete and absolute effect on what's happening here. So this can't be related. If there's a certain velocity here and a certain height, the velocity may change over here because the height has changed, but there is a relationship between the height, the density, and the velocity in point 1 and point 2. And it sort of says this. There's atmospheric pressure, there's the hydrostatic pressure that has to do with where we are with respect to height, and there's the dynamic pressure, which has to do with how fast things are going. If things are at a certain height and a certain velocity at point 1, then they will be at a certain height and a certain velocity at point 2. We can link these together real easy. And we can have a look at this when we look at positive pressure ventilation also, or just natural flow ventilation also. If things are happening here, if this size is this much and so, then we will need to have this at this end. Now, so we can relate this. It's going to take a few equations to get it done. Please bear with me. I'm not going to go through the equation. I'm just going to show you them. I'm just going to show them. So, and also we can apply this. If we have a positive pressure here, we just express the flow a bit differently. So I'm going to say that things are either to and from, okay? And the volume flow and the velocity from F, the volume flow and velocity to, so to and from. And I'm not going to go through the equation. I'm just going to sit down while I do this. So you set up the equations. I'm not going to go through this. You just set them up. You say this equals this, it must be this, Bernoulli told me, and so and so. And So we're not going to go through this. We're going to look at the situation as point 0. We're going to say that's equal to a situation somewhere here. And then we're going to move the height up, and it's going to be equal to some situation at point 2. And it's no magic. We just do this. There's a point to this. I will come to it. We do this. We start to find out that there is some kind of what we call a ventilation factor. There's a factor here that tells us that the area of the outlet opening has some relation to the area of the inlet opening. So this thing here has some kind of a value. What can this tell us? Well, it can tell us a lot. So I'm going to take this and check what it does. So this is the volume flow out of smoke. The volume flow of smoke out through the opening. And here is a relation between the area of the inlet and the area of the outlet opening. What does this look like? What does it look like? Well, when you draw it up in a curve, it turns out, let's see, when the area 2, the inlet opening, is much bigger than the smoke ventilation, then this factor will be very small. So if this is very big, or if this is very big, and something small divided by something very big, this is going to be 0. It's going to be very small. Okay. So if the 2 is really big and the from is very small, we're not going to get any flow. Okay. But if the from is very big and the 2 is very, this will be large. So let's put this on the x-axis and put this whole thing, the ventilation factor, on the y-axis, and we're going to call this the efficiency factor. And it turns out that if the vent area so if we say that the area from divided by area 2 is 1, so it means that they are equally big. So the area from is equally big as the area 2. Then this factor is 1. Now if we turn around and we say that the area from is only half of the area 2. So this area of flow coming in is twice as big as the area of the smoke ventilation going out. So that's when we're here. Then the efficiency of the operation is low. It's very low. So let's say if they're equally big, both openings, then the efficiency is somewhere around 70%. Now, if we go up to, if we make sure that the from ventilation is twice as big as the 2, then we're talking. Then we're up to 90%. After that, it doesn't really matter. Even if we increase and make the from ventilation extremely big, it's not going to help us a lot at all. It's not going to help a lot. So I would say that if you're going to create you're going to try to ventilate and you're thinking, how big? Then try to make the from ventilation twice as big as the 2, if you have a choice and you can see properly and it's not the middle of the night and a huge storm and stuff, which sometimes happens. But try to have it 2 to 1. So what happens when we so this is natural ventilation. So this is the natural ventilation. We're not using power, any positive pressure or anything like that. But now let's have a look at positive pressure ventilation. So we're going to put a fan out there, and we're going to push the air in. And if we have a very small outlet, we push the air in. This is far too small. Of course, we're going to have choked flow, and it's all going to come back. And but if it's very big, there's going to be no problem. It's just going to flow right out. Now I'm going to have a look at much more. This was easy, but if we have a complicated situation where we have many rooms and we're going to blow air in there, and let's say that we have a fire in the kitchen out here. A fire in the kitchen. We open that window. And we put the fan right here. We know that there's nobody in the house. So we're going to open up as close to the fire as we can, and we're going to put the positive pressure ventilation. So what's going to happen here? What's all this going to do? How is that going to complicate things? Well, and also another question we often get is, before we have a look at this, people ask me, how far from the door should I put my ventilator? And I have to say there's really no single answer. It depends on very many things, on the fan size, the type of fan, the construction of the fan, the size of the door, the layout of the building, and all kinds of things. So consequently, is before you sort of get to know you really should just test it a few times. There is no single answer. It should be 2 meters from the door. There is no single answer to this. I really tried to find the answer, but there are maybe rules of thumb. Don't know. So let's summarize. Pressure differentials create the flow. It's the pressure that completely controls the whole thing. Outlets should be at least as large as the inlets, preferably twice as large. More than that doesn't help. If they're equally big, we're running at about 70% effectivity. If they're twice as big, we're running at 90-something%. If there's no outlet, there's no point in the whole thing. It's just very dangerous. You increase the danger. If you don't have positive pressure ventilation, then it's going to take a long time to get rid of the smoke. But we often do this. We suppress the fire, and then as something to finish the job, we just clear the smoke out. And it's very difficult to do that without a fan. So we've been talking about a systems approach to firefighting, where a lot of different factors have an effect on what we do and in what sequence we do things. First do this, then do that, and so and so. And some very basic characteristics is we need oxygen or air, and it's a self-sustained process. It generates heat transmitted by radiation, convection, and conduction. Fire produces gases and particles, and fire gases have certain characteristics. Suppression interacts with the fire. It interacts with the process of oxidation also. It stops the combustion. It blocks radiation, reduces convection, it stops conduction. So heat transfer is stopped. Extinguishing media mixes with the gases and the particles. And so the characteristics of the gases and particles, they change dramatically when we start the suppression process. And if we look at ventilation, the venting will provide air to the fire. It's very difficult to check, is it fuel controlled, is it ventilation controlled? If it's fuel controlled, we're not all that worried. If it's ventilation controlled, we have to be very careful. And venting will interact with the generation of heat. It may cool things down, may stop the radiation and cool things down, get rid of the hot gas, but it can also increase the heat by increasing access to oxygen. And so venting will interact with fire gases and particles. It may remove gases, but it will also provide air to combustion. So these all things, what I'm saying is that this has an effect on that, and so and so and so and so, and it's all connected. If we do this, then that'll have an effect here, and so and so and so and so. And what we're basically saying is that this is a dynamic process. It's what I started by saying. It's a very dynamic process where many processes interact in a system, more like this. And it's very good to know about the basic physics, classical physics and chemistry that run the thing so that to help us make the right decisions. But ultimately, it is, of course, the firefighters or the fire officers' experience that does this. But if you know some of the physics and classical physics and chemistry, maybe you can get the experience a little faster. So it will help. But it's, of course, this is an experience-driven business, really. It's no good just knowing about reading all the books. You have to have had experience in this. So these are the two books that Stefan has sort of written, and this is the end of my presentation.